got the second part of today. We have the second part of transformations. So, how do transformations affect lines and shapes? Understanding the effects of transformations. Glad all of you are looking at your notes from yesterday. It's the exact same thing we did yesterday. Part 2. Okay.
No.
Yeah, true. Okay. So it's just different ways to look at this. Okay. First off, we have a reflection. A reflection is a transformation across a line called this line of reflection, so that the line of reflection is the perpendicular bisector of each segment joining each point and its image. So you might want to write this down underneath your notes on reflection. The line of reflection serves as the perpendicular bisector of each segment joining each point and its image. Okay? In yesterday's classwork, we worked a couple examples. I told you guys about this. I said, hey, if something is reflected across the x-axis, right, all that happens is the x-coordinates stay the same, and the y-coordinates, you take the opposite. So if this was positive y, it becomes negative y. If it was negative y, it would become positive y. See that, right? Think about what's happening here. I'm not changing anything as far as my x-coordinates go, but my y-coordinates are flippy-floppy, okay? Whenever I make a reflection across the y-axis, it's the exact same effect for the y variables, right? My height doesn't change, correct? Height isn't changing. Where I am on the y-axis won't change at all, but the x-coordinates are now playing flippy-floppy. Okay? Oh, and then there's the dreaded across the line where y equals x. And this is the one that'll mess you up, bro. Okay? This is the one that will, that'll probably needs the most attention. Okay? It is, it's can be difficult sometimes to see. So, help me out here. Joel, what do you think that point right there represents? I don't know. 2, 4. Sure. Good. 2, 4, right? That's at 2, 4. Okay, let's just say, remember, theoretical, practical, right? Theoretically speaking, it's simple. Yeah, whatever was xy becomes yx. Okay? Put it in practical terms. You started at this point P, and we said it's at 2, 4. Okay? If I reflect across the line y equals x, I will simply switch both coordinates. This point would become 4, 2. Okay? When you reflect across the line y equals x, you take your original xy coordinates and you rewrite them so that the x coordinate point is the old y and the y coordinate point is the old x. Okay? That's all you got to do. Flippy flop both. Okay? Alright, everybody get this part down. I need a little bit more time. Alright, back to lines of reflection.
Yes.
Alright, here we go. Oh man, how do we do this like freehand? Well, it's kind of the steps involved here, okay? First off, through each vertex, let's say we had a triangle. Don't worry about writing this. Just try and visualize it right now, okay? Alright? I promise.
Can you draw it?
You won't be doing this on the EOC, okay? I promise. They're going to put everything in a coordinate plane and make it really fun on you guys. All right, first off, how would we draw a line of reflection for any given shape? For each vertex. Remember? Angles, the vertex of each angle, if we put angles together, we get like a triangle or shape of some description. We could draw the perpendicular bisector to the line of reflection from each vertex. then, this is where it gets difficult. Measure the distance from each vertex to the line of reflection. So let's say this was, I don't know, 1, 2, 3, 4, right? On the other side of the line of reflection, I would go down 1, 2, 3, 4. If this was 1, I would go over 1. If this was 1, 2, 3, I would go 1, 2, 3, right? And then I connect the dots. I mean, that's literally what we've done here. We have connected the dots. It's a fun game, you know, crossword puzzles, whatever it may be, okay? Right? So to freehand a line of reflection, that's how you would do it. Now translations, they are somewhat trickier, okay? Translation is just a transformation along what we call a vector, such that each segment joining a point and its image has the same length as the vector and is parallel to the vector. Great. What does that mean, Mr. Hobbs? Okay. So yesterday we didn't, I don't think we got to this on the classwork, but you might see it at some point in time. They are called stretches. Okay. So if I have a horizontal translation along a vector such that A, it means that your image to, or your pre-image to image is getting stretched a little bit. Okay? You're not going to do anything with your y coordinates. You're just going to add A to your x. Okay? Let's try and visualize this.
What do we need about that?
You just need to pay attention right now. Okay? I start at the point 2, -2. I apply the following transformation. Let's go x plus 2, nada. It'll just say y. Okay? X plus 2, y. What do I do to the x coordinate? Add 2. What do I do to the y coordinate?
Nothing.
Keep it the same. That's how you would get 4, -2 as your prime point. Okay? It's called a stretch, or it's also called, you're going to see it more like this, any type of translation horizontally or vertically, you can do the same thing. Okay? That's simple. Notice, this is the translation that we talked about yesterday, and it's way easier to see, right? When you're moving left, right, and up and down. Okay? Those are the easier translations to see. Alright. You can do this, and this is kind of the example I'll give you guys about translating along a vector. Right? A line parallel to the vector through each of the vertexes of, well, this isn't a triangle, okay, of any shape, okay? And then you're going to measure, just like you did before, measure the length of the vertex from each vertex, mark off the distance in the same direction as the vertex on each of the parallel lines. Next problem, what do you make? Here we go. From each of the vertices, how far was it? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Whatever it was, right? And if I wanted to recreate this shape, I would do so right here. Right? Okay? Question. See how well our understanding is. You don't get me. This now I won't lie. If you get it right, it's probably going to be done today. Okay? Is this shape congruent to that shape? Do what? Yes. So if you said no, because you didn't know, it's okay. Your instinct says no. And then your gut says yes. Why do you want your gut to go over your instinct here?
We can get a total lock.
Always trust your gut.
Nope.
Always
trust believe your first instinct always.
Reply for the bachelor. Right? All translations, reflections, and rotations are what? Congruent transformations, identical transformations, rigid transformations, right? Rigid motion. If I translate anything, it always will keep the same shape and the same size. Okay? So that's the part that you got to see. I know it might look like these two aren't congruent, but geometrically speaking, not what your eyes see, but geometrically speaking, they have to be congruent because you apply a translation. Okay? All right. Last thing, rotations. Okay? This is probably the one I'd write down of all the slides today. This would be the one to write down. Yeah, just this one. Okay? And this is it. Yep, because I don't even worry about the other one. All right, here we go. A rotation is a transformation about a point P called the center of the rotation such that each point and its image are the same distance from P and such that all angles of vertex P formed by a point and its image are congruent. Don't worry about writing that down. Worry about the good stuff. Right here. Copy that chart down. Okay? Copy. Write the chart down. Okay? Write the chart down. Here we go. Rotations in the coordinate plane. If I rotate 90 degrees about the origin. Okay, first off, if I go from point P, and look at here, P prime, and it's going this way, am I going clockwise or counterclockwise? Counterclockwise. Which way does the clock tick?
Clockwise.
To the right. Thank you. Very good, Mr. Knapp. Count on you. All right. Now, if this goes to the left, okay, or to the left, then it's going counterclockwise. Of course, unless you're going from quadrant 3 to quadrant 4, or 4 to 1, and then it's really going like to the right and it's going up. So you can't think of it that way. But in this case, it's going counterclockwise. Okay? Mr. Hobbs, how in the world do I know what to do? Well, you can apply, if you get really good at this, okay, if you get really good at these rules, you're gonna be A-okay on this first test, okay? Zima, count me off here, ready? 4. Okay, so this, let's just say, is at the point 4, 3. Alright? Here's a little trick you can do. Take your y, your original y, the opposite of it will become the new x. Take your original x. Nope. The regular original x becomes the new y. Okay? So, are you sure, Mr. Hobbs? Steven, count it off. Ready? Here we go. Yep, I'm sure.
How'd you get the negative?
So because you're rotating about the origin to the left, right? Because I'm going to the left, I'm going to start with this original y point. But when I'm doing this rotation 90 degrees to have a full 90-degree rotation, I look at how far did I go up, and that's how far I'm going over. I know it's weird. It goes all the way back to what you learned when you talked about slope, okay? Rise over run. Oh no. You just gave me the death. You gave me the, I don't know what that means.
Yeah.
I don't care who you had. Okay? I don't care who you had. Rise over run. It's easy and fun. Rise, the change in y over the run, the change in x. y2 minus y1 over x2 minus x1. Well, the problem is that we're going the other way now, right? Okay?
Now you're kind of like Skyline.
Oh, sure. Okay? So that's why I do that, okay? So I can just look at, if you memorize this rule right here, you'll be okay with all rotations. Okay, all rotations, you'll be okay. All right, the last one's easier, 180 degrees. Okay, 180 degrees, probably the easiest one we can do for you. Okay, let's say it's the new coordinate points. Let's say it's 1, 2, 3, 1, 2. Let's just say it's 3, 2. Yep, nope, it'll be negative 1, 2, 3, negative 2. See, and then not, yeah, in a 180 rotation, you don't have to flip x's and y's. You just have to take the opposite of each. Okay? You just take the opposite of each. So this is your rule for 180. Here's a 180 degree rotation. Here's a 90 degree rotation. All right, now, who said, I don't know who said this earlier, I said it wrong over there. Get it right now. When I rotate a figure, is the pre-image congruent to the image?
Yes.
Okay, right? And congruent means what?
Same.
Identical. So if I ask you a question, because you're going to get asked this question on next week's test, okay? If I ask you a question about, hey, triangle PQX is translated, and then it's rotated, and then it's reflected, and then it's translated, and it goes through 800 million transformations that are all congruent transformations. The question would be, the length of PQ is or is not congruent to the length of P prime Q prime.
It is.
Has to be, right? The size doesn't change. The side length of the triangle before the transformation is the exact same after the transformation. Okay? That's the big idea of this whole unit. Alright? Any questions on this? Cool. Guys, we'll work. I'll get these graded. We will work. I know.